purpose of this video is to give you a little more background and show more examples of IR spectroscopy. And so far you have identified unknown organic compounds through either chromatographic or physical methods. For example, you used TLC to identify a mixture of analgesics. You used melting point to figure out whether your PK1 or 2 was acid amylid or phenacetin. And you used boiling point to figure out, for example, if you were distilling 95% ethanol or water. And all of these are what I like to call comparative methods, meaning that you can only use them to identify a compound if you have something to compare it to. So, for example, you know the boiling point of the azeotrope of water and ethanol. So that's how you could identify that. You were able to look up in a database like Merck Index what the melting point of phenacetin and acid amylid were. You were able to have authentic samples of, say, aspirin and salicylate and other caffeine and other compounds to compare on the TLC. So you have to have either a listing, a database, or you have to have the actual compound in order to identify unknowns by these methods. On the other hand, over the next few weeks, we're going to be discussing spectroscopic methods for identifying organic compounds. Specifically, we're going to be looking at infrared spectroscopy, nuclear magnetic resonance spectroscopy, and probably early next semester we'll look at mass spectroscopy. But the key thing is they all involve how organic compounds interact with electromagnetic radiation. And just a reminder, here's the electromagnetic spectrum. We're going to talk about this more in a second, but it goes from, low energy radio waves to high energy gamma rays, and right here in the middle is our little bitty visible spectrum. So what kind of information can you get from spectroscopy? Well, infrared spectroscopy can basically tell you what kinds of functional groups are present. It can also be used in a comparative way when you might look up a matching spectrum in a library. And the Royal Society of Chemistry video talked about the fingerprint region, and that's very useful in matching spectra in that way. NMR can tell you the kinds of hydrogens and carbons in a molecule, which is great for organic molecules, which are mostly carbon and hydrogen, and it can also tell you how they're connected together. So it's a really important method that we'll talk about a lot. Mass spectroscopy can tell you things like the molecular weight. It also can tell you some things about structure, such as whether a molecule has a methyl, ethyl, or benzene groups in it. It's also very, very much used as a comparative method. For example, if you've ever heard about drug testing in the Olympics or other big sporting events, though athletes are submitting blood and urine for GCMS analysis, which tells them if they have metabolites of forbidden drugs in their bloodstream. Finally, UV-Vis historically has been used for structure determination, but it's primarily used for quantitative analysis, as in it'll tell you how much of a particular compound you might have in a solution. As you saw in the RSC video, bonds in covalent molecules vibrate when they absorb infrared radiation of a specific frequency. So that's what's happening during infrared spectroscopy. Other spectroscopic methods, such as NMR, that's not affecting the bonds, that's actually affecting nuclear spin. And mass spectroscopy actually breaks the molecule apart. That's a very high energy method. It just smashes the molecule to pieces. And UV visible spectroscopy, that primarily breaks pi bonds, and so it's intermediate in energy between NMR and mass spectroscopy. And here's our electromagnetic spectrum again, and just as a reminder, you can see that the energy of the electromagnetic radiation is increasing going to the left, and you can see that we have the frequency here in hertz, and as the frequency increases, the energy increases. Recall that E is equal to Planck's constant times the frequency. Also, you can see that the energy increases as the wavelength gets shorter and shorter, and recall that The energy is equal to Planck's constant times the speed of light divided by the wavelength, so that makes sense too. We're going to talk about infrared radiation primarily in terms of frequency. And the unit that we're going to use to talk about the absorptions in the IR is called a wave number. And the wave number is directly proportional to frequency. You can see here how it's derived, but you don't really need to worry about that. The key thing that you need to worry about is that as the wave number gets larger, that means the frequency of the infrared radiation is larger, which means that it is higher in energy. And the spectral window we're going to be looking at, you can see right here, is from 4,000 to 400 reciprocal centimeters, which is another name for a wave number. And here's what a typical infrared spectrum looks like. This is the infrared spectrum of ethanol, which has a alcohol functional group. And the x-axis here is the wave numbers. And the y-axis is something called percent transmittance. So when the infrared radiation is passed through the sample, if the percent transmittance is close to 100%, that means that the sample is not absorbing any infrared radiation or very little infrared radiation at that frequency of light. As we proceed through, and we generally look at these from higher frequencies to lower frequencies, what we can see is for ethanol, as we go through, all of a sudden, at about 3,500 reciprocal centimeters, we get a really, really large absorbance. It goes almost down to 0% transmittance, meaning that the compound is absorbing very strongly in that region. And that absorption is due to the OH bond in the alcohol, and part of the reason for that is because very, very polar bonds give you very, very strong absorptions. As we continue to go through, we can see that we have another peak right about here, and that is a pretty strong absorption, also almost 0% transmittance. And that peak is due to a CH bond. And that's, you might be saying, well, Ann, that's not a very polar bond. Why is it such a strong absorption? Well, in most organic molecules, you've got a good number of CH bonds, and they're all absorbing at roughly the same frequency. So usually, but not always, the CH absorbance is a pretty strong absorbance. And after that, I'm not going to try to look at every wiggle and peak in this particular spectrum. One of the things you do with an IR is you want to zoom in on certain parts of the spectrum, and as you might recall from the RSC video, this part of the spectrum is often referred to as the fingerprint region, and we don't try to interpret every single peak in this region. So this is a nice slide that shows you where to find some of the major IR peaks or absorptions for different functional groups. So if you have an alcohol or carboxylic acid, those both contain OH groups, an NH peak, such as in an amine or an amide, you're going to expect to see an absorption above 3,000 reciprocal centimeters. You're always going to see CH right there around 3,000, and that's CH if it's a sp3 hybridized carbon. If it is a hydrogen attached to an sp2 or sp hybridized carbon, it's going to be just above 3,000 reciprocal centimeters. Another really, really important stretch is around 1,700 reciprocal centimeters. It varies a little bit. That is the carbonyl stretch. That's a very strong stretch, and it's one that, as you know, carbonyl appears in a whole lot of functional groups, carboxylic acid, ketones, aldehydes, esters, amides. So that's a really, really important absorption. This slide's nice because it kind of helps you focus in on where to look in the IR for information. In this region from, above 2,600, the NH and the OH peaks are really, really indicative of functional groups containing those types of bonds. As I said, all organic molecules have CH, so that's not super helpful, but that's the region that you find it in. Also, in between, say, roughly 1500 to 2000, that's where you find that carbonyl stretch, which is really, really indicative of a lot of different functional groups, and also a CN and a C double bond C stretch. You can also find that in those regions, but this carbonyl one is really, really important. Also, this region from about 2000 to 2600 is very nice because there's not a whole lot of stuff there. And so if you see something there, you know you have a triple bond, either a CN triple bond, which is called a nitrile, or a C triple bond C, which is an alkyne. So that's a really nice indicator of certain functional groups. Okay, so now we're just going to take a look at a couple of different spectra, just to give you an idea of what they look like. Here's the spectrum of pentane, not very exciting. The main thing that we're seeing here is all of the CH bonds, and the rest of it is pretty much fingerprint, and we're not going to spend a whole lot of time looking at it. Here's the IR spectrum of 1-hexene, which contains a double bond. And you can see here, notice we've got this sp2 hybridized carbon-hydrogen bond, and then we can see that there is now an absorption just a little bit higher than 3000, and then the rest of the CH bonds are absorbing just below 3000. You could also say that, oh, I'm seeing a C double bond C right here, an alkene. Those are usually a little harder to pick up, but that is a good place to look when you're trying to figure out what functional groups might be present. This is from a website called Animated Spectra that's hosted at Ohio State University, and this compound that you're seeing the infrared spectrum of is 2-butanone, which has a ketone functional group. So it's got two kinds of bonds. It's got carbon-hydrogen bonds, and it's got a carbon-oxygen double bond or carbonyl group. And we can see that here around 3000 there are CH bonds, and right here just above 1700 reciprocal centimeters is our carbonyl group. Now, Animated Spectra, I've posted a link to this website in Canvas, and here's a screenshot of the landing page for Animated Spectra. And so you can see, and there's many more functional groups if you keep scrolling down, and you can click on any of these and see a spectrum. And another really cool thing that you're going to see is here in this example is acetophenone, and we're going to be able to see the carbonyl group, carbon-hydrogen stretches. There's the carbon-hydrogen stretches. So you'll be able to see those. You also see there's carbon-carbon double bonds in this molecule, and they're going to be in this region. And when you look at the spectrum, one of the things you can do is you can click on Show All Highlighted Regions, and it's going to look like this. And that means that you could click right there, and you're going to see some of these CH bonds start to stretch and move. And if you click right there, you're going to see this carbonyl start to stretch and move. And the same thing, if you click right there, you're going to start to see the double bonds in the aromatic ring stretch and move. So try it. It's really cool. So what you're going to be doing this week in lab is you're going to be using infrared spectroscopy to analyze and see if you did isolate a carvone from either the spearmint or the caraway seeds. You can see there's the functional groups that are in the carvone are, we've got a ketone or a carbonyl group. We've also got a couple of alkenes that we should be able to see. Remember that because these are enantiomers, they're going to have exactly the same infrared spectrum. So we won't be able to tell the difference between the two enantiomers, but you will be able to tell if you did indeed isolate carvone. In addition to looking at the two functional groups, the alkene and the carbonyl or ketone. One of the things we're going to also be doing is we'll be looking at the fingerprint region, because what you're going to do is you're going to overlay your spectrum with an authentic sample of ketone. So you'll be doing a comparative method, also using your spectroscopic methods. And Dudley hopes that you took good notes during the videos, because you are going to have a quiz in Canvas that you'll need to complete before you come to lab.